Welcome to 3 Steps to Sketch. In this video, we're going to graph the basic unshifted cosecant graph, y equals cosecant 2x. So here's our template and our grid that we'll use for our graph. And as we start, let's notice that our equation is in the general form y equals a cosecant bx. And that's how we know that we're dealing with an unshifted cosecant graph, and we can use the basic cosecant template. So we'll get started with step 1. We'll find the companion equation and its essential information. So the companion equation is simply the reciprocal equation. We'll just replace cosecant with its reciprocal sine. So all you have to do is write the companion equation as y equals, we'll use sine instead of cosecant, 2x. So we'll graph sine 2x first, and then we'll take the reciprocal of that graph to get the graph we actually want, y equals cosecant 2x. All right, so let's dig into the companion equation. We'll analyze a little bit so we can get a good sketch of that. A, we see, is an understood 1, the coefficient in front of sine. That means our amplitude is 1, or that's the distance from midline to maximum or midline to minimum. B is 2, it's the coefficient of x. That tells us we'll have 2 cycles of sine or cosecant between 0 and 2 pi, and it also helps us find the period, and we do that calculating 2 pi divided by b. So 2 pi divided by 2, our period is pi, or the length of one horizontal cycle. So now that we know that, we can choose some appropriate labels for our axes, and we're very particular about the horizontal scale. We want to take the period and divide by 4. So pi divided by 4. That's how we'll label our horizontal tick marks. And what that does is when we plot the companion pattern to get us started, each main point will align with our horizontal tick marks. So it'll make our graph nice and clean and accurate. All right, and then for our vertical scale, let's choose 1, and that should work well. So let's take a moment and go ahead and label our axes. So we'll start with the horizontal axis, count by 1 pi over 4. So we have 1 pi over 4, 2 pi over 4 reduces to pi over 2, 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4 reduces to 3 pi over 2, we have 7 pi over 4, and 8 pi over 4, which reduces to 2 pi. So if you're working along with me, go ahead and pause. I'm going to do that as well, and we'll label the negative side of the horizontal axis. All the same values, just negative. So this is what your fully labeled horizontal axis should look like. And let's take a moment and label the vertical axis. So we're just counting by 1 for each of those. So we have a really nice clean setup. Now before we move on to step 2, let's take a moment and find the asymptotes equation. So these are going to be the asymptotes of cosecant 2x, and they'll occur wherever our companion graph has its original x-intercepts. And so a quick, easy way to do this, and I will post videos that go into a lot more detail on this, just specifically looking at this topic, but all you have to do to find the asymptote generating equation for a cosecant graph is take the inputs of your cosecant function, so 2x, I'll do a little scratch work up here. So take your inputs and set them equal to where sine x has its original zeros. So that's at 0 plus pi k. And k is just an integer here. We'll talk a little bit more about that in a moment. So now we want to divide everything by 2 to get x isolated, and we'll write that down in the space for asymptotes equation. X equals 0 divided by 2, of course, is 0. Add that there. So we have 0 plus pi over 2k. So a little bit more on k. Substitute in different integers and it'll give you a different asymptote along your cosecant 2x graph. So for example, if you let k equal 0, there should be an asymptote on our final graph at x equals 0, or on the y-axis. Let k equal 1, we should have an asymptote at pi over 2. Let k equal 2, you should have another asymptote at pi. You can let k be negative 1, there should be one at negative pi over 2. So hopefully that helps you see a little bit how this works. It's a really concise way of representing all the asymptotes of a graph in one equation. So now that we have that asymptotes equation and kind of have a way to double check ourselves as we're getting toward our final graph, let's go ahead to step 2 where we're going to plot our companion pattern. So we're basically graphing our companion equation sine 2x. Remember that the sine pattern, the base pattern, is x-intercept, maximum, x-intercept, minimum. Okay, so we'll do that starting at the origin. So lightly mark this graph. This is not our final graph. I'm going to represent it in light blue. We have 0. Our maximum happens at our first labeled horizontal tick mark, and the y-coordinate comes from our value a. We talked about the amplitude at the beginning. Then we'll have another x-intercept at the next horizontal tick mark. Then we'll have a minimum at the third horizontal tick mark at 3 pi over 4, and the y value will be the opposite of a. All right, then we'll close that graph off. That point would represent the start of a new cycle. And you can see here is the graph of our companion graph. This is y equals sine 2x. So now we're to the fun part. Step 3, we get to recip, sketch, and repeat. So recip just means take the y values and take the reciprocal, and that will get you from the sine graph to the cosecant graph that we actually want. Now, you may be familiar with what a cosecant graph looks like, and after you've graphed a few of these, you'll just know what this pattern looks like, but we will walk through and just talk about a few values, a few specific values, and how we get the reciprocal. So starting at the origin, if you try to take the reciprocal of 0, well, you'd get 1 over 0, which is undefined, and that's how we know we have a vertical asymptote here. And that's the vertical asymptote that we were actually talking about not too long ago. When k is 0 in our asymptotes equation, we get this asymptote represented at x equals 0. All right, so now let's take some reciprocals. As we move to the right, let's say we're taking the reciprocal of 1/2. That's 2. The reciprocal of 1 is 1. Another 1/2 as we keep moving right turns into 2. Okay, and then we get to the 0 or x-intercept at pi over 2. Same thing happens as before. We cannot take the reciprocal of 0, so we know there must be a vertical asymptote there. And that's the asymptote that comes from our asymptotes equation when k is 1. All right, let's keep going. The reciprocal of negative 1/2 is negative 2. Of negative 1 is negative 1. Another negative 1/2. The reciprocal is negative 2. And then as we get to pi, we would have another asymptote there. So let's take a moment. This is one cycle of our final graph, y equals cosecant 2x. Let's go ahead and sketch this so we see what it looks like. We have part of the curve here and another part here. This is one full cycle, and we see it happens in the space of pi. And now that we have one cycle sketched, we can simply repeat this over and over for as many cycles as we need. So we know we have an asymptote at pi. This was when k equaled 2 in the asymptotes equation. And then we just repeat the pattern over again. So we really just need to plot probably this point at 5 pi over 4, 1 to know we have a curve like this. We'd have another vertical asymptote. We didn't actually find this one, but hopefully you can see if you let k equal 3, you would generate this asymptote. And then we have another curve. This one we say it has a local or relative maximum. And notice that this one happened because of that minimum from our sine companion graph. Just an interesting thing to note. Okay, we'd have another vertical asymptote here at 2 pi. That's when k equals 4. And now let's go in the other direction. So we're just repeating this pattern. This time we're just working it backwards. So it's curve that has the local maximum. Asymptote that comes from when k is negative 1. This is a local minimum for the graph. So local or relative. Okay, we have another vertical asymptote at negative pi. That's when k is negative 2. Another curve that has a local max. Another asymptote at negative 3 pi over 2. That's when k is negative 3. You are probably seeing the pattern. And we have another asymptote at negative 2 pi. So this is 4 cycles of our graph y equals cosecant 2x. Notice you can still double check some of the information. Say you wanted to go back, and we've been checking the asymptotes along the way, but say you wanted to look again at b. We know B is supposed to tell us how many cycles happen between 0 and 2 pi. And so you can see we have one cycle here in green and then a second cycle here in purple. And so that should just make you even that much more confident that you have an accurate graph for y equals cosecant 2x. So this is the 3 steps to sketch method for basic cosecant graphs. Hopefully this helps you understand the method even better and feel confident to graph any other cosecant equation that is thrown at you. I'll post links to more worked examples in the video description, as well as some other trig graphing examples, so feel free to check those out, and thanks for watching.